Great. To keep the atoms in place while they scatter light. But the other aspect that was also certainly enabled with this microscope technology is a new level of control over these systems, local control by using this light shaping techniques via a digital mirror device or spatial light modulators based on liquid crystal displays. So you saw already some talks. Two of the pictures I show here you have seen already. Wasim's talk about the non-equilibrium dynamics in the model and the spin transport, charge transport it was for Wasim, and Martin's talk about the about the spin transport. And Wasim didn't mention it, but both of these actually use these potential shaping techniques. In this case, it's clear to flatten the box. In this case, it was also kind of to, where's Wasim, to create a flat bottom trap to make the system kind of cleaner. These results, you also seen the nice anti-ferromagnetic correlations already in the other talks you mentioned from Marcus's group. Where also it's the interplay of the observation and the control that enables here cooling to record low temperatures. And actually, since the last part of the title of the workshop was the low temperature frontier, I want to at least mention that here where we stand with these microscopes, and we are standing there. So we are standing, Marcus has roughly 0.25 T over T. Wasim is very close without actually potential shaping. 0.3. Martin here with potassium, that's a bit harder it seems than lithium, is around 0.9, but I mean there's also not a huge difference. I mean, one could say we are in all of the systems still quite hot. So we are around, so this is about around 0.3 kb for the fermions, and that's where basically roughly we seem to hitting some limits. I think we don't really know where the limit is. Might be evaporation, and but if you compare that actually to what has been reached with the bosons, single spin component bosons in dense temper currents group, so they have something like 1 per mil of kb in terms of entropy per particle. So on the ultra cold frontier, we have something to do here, and the question is where actually the limit is. It's not too clear to me which limit we are at the moment running in, and I will report our temperature. A few slides later, our temperature will be for 1D systems, and it will turn out actually that is actually quite the same as they have here. In this talk actually I was emphasizing the local control, but of course with these ultra cold gases we also have very nice global control in a sense that we can basically choose the lattice that the atoms see quite at will, and over the past quite some different structures have been demonstrated here. Let's start with 2012, then Stamper Currents group, the Kagome lattice, then in Zurich, Tillmann's group. Actually quite tunable geometry from checkerboard, triangular dimer, and so on and so forth. Hexagonal lattices in Hamburg, and quite new quasi-crystalline structures in Cambridge, the other Cambridge, in Uli's new group. So we have quite some freedom to play with. And why I bring up this slide, because of that is a specialty of our Fermi microscope is actually that we play with non-conventional and slightly more complex lattice structures. The lattice structures we play with are actually super lattices. So that's actually the oldest of those kinds. They have been invented like in Trey Porter's group in 2006, and then shortly after Simon should also be here somewhere used them also in Munich. And how we create those super lattice? We actually have them in we actually have a 3-dimensional super lattice, but we are not using actually, well, mostly not 2 of them. There's just too many knobs you can play with, you know. But so how do we generate it? We actually generate it by kind of a spatial Fourier transform. But so we send in a pattern of beams that looks like that into our microscope objective, where basically this beam and this beam, so the outer 2 beams, are phase coherent to each other. Those are phase coherent to each other, and the same in the other direction. And we have a way of controlling the relative interference phase between those pairs, which sets basically the symmetry of the lattice. Then when we send basically this You see, I mean, it's basically different k vectors into the objective. In the atomic plane, the image plane, we create such a nice superlattice. And to mention here is something special that is enabled by the use of lithium. We can use quite large lattice distances here, which greatly simplify actually the imaging that we do later on. And how do we do the imaging? Actually, that's another quite specialty of our experiment. We don't image directly in the superlattice. We actually have an additional three-dimensional lattice that we can make extremely deep, as required for lithium, with which we actually oversample this, what we call physics lattice here, by at least a factor of 2 in each direction. That enables, for example, also non-parity projective imaging in our system, because we can separate basically the atoms before imaging, and all of these tricks we can play. It comes with quite a price, I would say. So in that lineup of experiments, I guess Wasim is basically the simplest, which is very good, not bad. So don't see this as a and our ones is on the other side, at least in terms of laser beams that hit the atoms in the end. Yeah, so that's the price you have to pay. Good. With this, we had already yesterday this showing up. We can also make nice images, and you see here already that we can basically play with different structures. So this here is basically a mod insulator in a what we call short configuration. You clearly see we nicely resolve the individual sides here, or we can play with a long short configuration where basically the y direction here is double the spacing. And I will basically exclusively talk about this configuration, but both in 1D and 2D. In 1D, it will basically that we decouple the chains in. Well, basically the motional degree of freedom is this direction, while vertically it's completely decoupled. Or we just choose the lattices such that we have effectively isotropic hopping, even though the underlying lattice is non-isotropic in the system. That's how we do 2D at the moment. And why are we doing this? Because it gives us a nice imaging technique. And this imaging technique basically enables us to image the spins and the charges, the density basically, in one shot completely. In the sense, so you can say we measure basically all 4 local basis states of the single band Hubbard model. And how does that work? That works just by a local Stern-Gallaugh splitting. So we use this Y superlattice such that under application of a magnetic field gradient in Y direction, we basically force the spin atoms, the spin down atoms to go down locally in this lower well, and the spin up atoms to go up. And with this basically before the light scattering, which basically erases the spin information on the atoms, that's why we have to encode that basically the spin information before spatially, we get basically a full reconstruction. So here basically you see these 5 1D chains. And along each chain, we can now basically check what is the population. So we see here's no atom, then we have here spin down, spin up, and so on and so forth. This here is a doublon. So you see basically we can map basically everything. And that gives us the possibility to calculate now directly correlation functions between charge degrees of freedom and spin degrees of freedom. And that's basically the basis of all the results I'm telling you today. So let's start first. Well, I think I still owe you the temperature. So how do we get the temperature? The temperature we get basically from comparison, in our case, to QMC of l'eau de Paulet in the half-filled case. That's where we have done it so far. So that's basically, okay, we study Hubbard model at half filling, and all of you know basically the ground state of the Hubbard model at half filling is anti-ferromagnetic. It's very easy to understand. If you have a ferromagnetic order for fermions, basically any motion is Pauli blocked of this middle spin. If it's anti-ferromagnetic, it can win, the middle spin can win a little bit of kinetic energy by virtually hopping around. That's just costs you U, but it's not fully forbidden by Pauli blocking. And that gives you then in the end like the anti-ferromagnetic configuration with the spin exchange energy scale 4T squared over U, which is, by the way, in all our parameter regimes never really much larger than the hopping energy scale. That's also something that will become important that we basically neglect in our polaron story I'm going to show you later, but this ratio is typically 2 or 3 something for the cold gases, at least in the regime where I think we all are working at the moment. Good. Here comes the temperature. So what you see here is basically our 1D anti-ferromagnetic correlations versus distance in the half-filled case, where we can nicely compare now to QMC. QMC actually is the purple crosses behind the data point. So we have a very very good match here. Don't ask me why the crosses are not there. I couldn't find them in my plot this morning. But okay, so maybe the jet lag. So no, I checked actually. Whatever. We have quite good match, and if we match that. And also, what's usually quite a good match is actually, so the everyday workhorse to make a match with the theory is basically this nearest neighbor correlator. And what we find then is actually in 1D a temperature, which is basically the same what Marcus sees or what Wasim sees. So we are around 30% of T, corresponding to 0.4 kV entropy here. Well, I was citing already, of course, in 2D. There are also experiments in the same regime. So let's make the story a bit more interesting. Let's dope, and let's dope first 1D Hubbard chains. So what does the charge sector wants to do in the Hubbard model if we give it any degree of freedom, if we add a little bit of holes or doublons? Well, obviously it wants to optimize its kinetic energy. It means basically the charge-ons, the doublons, or the holes, they want to maximally delocalize. The spin sector, we have discussed it already, the spin sector wants actually anti-ferromagnetic order. Based on this, basically, we can ask the first very simple question. What would you expect as a spin alignment in the ground state of the 1D model around holes? Just a local spin alignment. Would it be anti-ferromagnetic in the sense that you fix the hole and you look to the left of the hole, to the right of the hole? Are the spins anti-aligned or are the spins aligned? Well, in this, if I just picture this, it's maybe not clear, but if you think about the hole wants to delocalize, then I basically have to add to that picture here basically the wave function of the hole being or the configuration of the hole being at each and every position, and then you see basically if you have aligned spins, you basically pay the price of energy J. And what's interesting here is basically if there would not be a hole, what spin would you put here? You would put a spin up or a spin down. You would always pay this energy price. So, and if you put here a spin up, you would, what I was going to explain now. No, I'm lost. Sorry. If I would put here a spin down, basically, then the system is happy. But you see, basically, that means basically if you have a fully filled system, then you basically have this parallel alignment at a distance 2, but here you would have this anti-parallel alignment. And that gives us a way of actually spectacularly comparing this in the microscope. So now making use of actually that we can really identify where the holes are. We can directly see a really drastic change of the nearest neighbor spin alignment around the holes, given if there's a hole or if there's not a hole. So basically this distance 2 spin correlator conditioned on having a hole really completely changes sign. And the error bar, it's really now too small. It's somewhere behind the points hidden here. And that's this effect on the local scale. We can also ask basically what do these holes do to longer ranged correlation in the system? Well, first of all, I said already, if you have a spin in between or you don't have a spin, that basically changes the alignment of those spins. But if everything is nicely anti-ferromagnetically ordered, it will also change basically the alignment of all other spins that are coming behind. Otherwise, you will have another spin on in the system. That means basically this hole being here flips the alignment of this whole block of spins here. The next hole flips it again, and everything is nice again here, yes? So that means basically now if you have a fluctuating hole number there and you measure, for example, a correlation between here and here, you see basically I have spin down, I correlated with spin up, spin down, and both of them, and that will average somehow to 0, yes? But how can we fix this? Well, in 1D, we can fix this by calculating actually, or by measuring non-local correlation functions, for example, string correlators, and actually exactly the same string correlator by which you would detect a hidden topological order in the Haldane phase of spin 1 systems, for example. So what we can do is basically, we can go through the whole chain. Let's say we want to calculate the correlation between 2 and 8. We go through the chain, we start at 2 with a spin down, we look at side 3, there's an empty side. Oh, we take this into account by a -1 means we basically, artificially flip the spins of the next block because we expect actually this now being flipped because the hole is there. until the next hole, and each and every hole gives a -1. So basically that's this formula. And if we do so, we basically can take out the effect of the holes in the 1D chain. So let's compare. What I show you here is basically the direct 2-point correlator versus distance. So the just standard 2-point correlator, you all know, in a condition where we have actually strongly fluctuating hole number. You see basically it completely washes out any staggered anti-ferromagnetic signal here. If we add now, or if we analyze this now in this non-local string correlator, we completely recover basically the magnetic hidden correlations here. So this works very nicely in one dimension. There's another way of doing this, and that's a very intuitive way that helps us also now. Well, I maybe comment on that on the very end slides where we basically measure now spin-charge separation dynamically. And that's basically by going into squeezed space. What is squeezed space? Well, that's the very intuitive construction, given that you know the spin and of each and every electron or atom in the system. Basically, the idea is, well, let's just forget of those sides that have holes. We just squeeze them out. You just make the spin shorter, the chain shorter. So now you see now in this squeezed space, there's no notion of holes anymore. We are talking only about spins. So how should we describe the system in squeezed space? Well, there are not many possibilities. We just describe it by a Heisenberg spin model, and that's all what's there. And then there's another aspect that's important, especially because we are of course at finer temperature in the experiment. You know, if I have one spin there in the wall and the other spin there in the wall, then they very rarely see each other, yeah, because they have a lot of empty space in between. That means basically this J, of course, becomes renormalized by the density here. Basically, that's the only effect that the effective squeeze space spin sector sees from basically the charge sector. We can again test this in the experiment, and now basically by binning our data a little bit different, instead of throwing everything together, we can bin the data in fixed doping sectors. So around unity filling here, the green data, we see the nice antiferromagnetic oscillations here. In lower density, you see basically those start to be damped, and we don't see the oscillations anymore here. And now let's go to squeeze space, and we see in squeeze space the system actually really doesn't care for the holes. So that's a way of seeing spin charge separation, in a sense that we see that the spin sector measured in the proper observables doesn't care for the charge sector really directly on the experimental data, and in a very I would say in a way that's really only available in those quantum gas microscopes, because you really need non-local correlators to uncover that, and there's no need of doing any dynamics. You see that directly on the equilibrium state. Good. I was emphasizing here already kind of that if you are interested in the spin order, you basically sit on the spins, you forget about the holes, and then you just check the spin alignment of each and every atom. We did new measurements in this picture where we actually wanted to see the effect. If we just take the standard 2-point correlator and now dilute the system a bit, then that basically leads to a stretching of the average distance between the different spins. And that means basically that if we can detect any remaining antiferromagnetic signal in a doped system, that actually leads to a stretching of the wave vector of the antiferromagnetic correlations, just proportional to the density. So those correlations are actually, it's 2 times the Fermi wave vector. So they go proportional to the density. And the picture is really just you dilute the system. And that leads then to incommensurate correlations, where basically the magnetic antiferromagnetism becomes incommensurate with the lattice spacing. We tested that. Basically now you see we have here basically a log scale on this plot, because of, if we have holes, we also have fluctuating holes. So if we pay a price, it suppresses the amplitude of the correlations that we see. And for comparison, I show you here basically the signal at half filling, and now we show here the signal at 0.7 filling, and we clearly see the wave vector becomes longer. If you don't believe it, that's our FFT signal of basically those correlations versus doping, and we clearly see here this branch going down directly linear with the density, or proportional to 1 minus the number of folds, actually as expected by Lagrange theory. And that matches very nicely. We can do the same actually for doping. for doping, sorry, for polarizing the system. So we can just sprinkle excess spins into the system, and those excess spins, they also cause basically the remaining spins to become more dilute. The signal you see here directly again. So we have basically blue is blue is basically no magnetization. Red is finite magnetization. We see a stretching of the signal. We can analyze this slightly different here, just to have a nice also check of the linear behavior in terms of fits. So when we plot here basically the magnetization versus the wave vector we extract, we see a very nice linear behavior. And in terms of the wave vectors, the amplitudes are quite different actually. But in terms of the wave vectors, the holes really behave very, very well. In this equation, really the same as the excess spins by really just diluting the system, like the carriers of these anti-ferromagnetic correlations. We can also, just for completeness, I want to show you here again for the magnetization case, the FFT. So that is basically in the magnetization case, the two linear fans. You see it's not very clean. There's always some kind of weight at zero wave vector. That's basically, well, it's probably, I mean, this is so broad is likely because we look at short systems, but one has basically to extract this nice linear signal, we have to set ourselves on this. We have to bias, so to say, ourselves a little bit to go on this out-fanning fan, basically. But that's exactly the same, actually, that we see in exact diagonalization theory here. So that's a property, basically, of the system as such, and not an imperfection. Good. How am I doing in time? You're doing well. I'm doing well? Good. That gives me basically, I keep that in mind. That's good. So I don't want to know the number. Good. 2D. 2D. So I talked a bit of, quite a bit on 1D now, and that was basically kind of old results. What is really exciting now is the 2D story. And from now on, you see a preliminary label on my slides because that's really what we are analyzing still. So what happens in 2D? In 1D, I showed you basically that we can make basically spins and charges simultaneously happy. Yes, we can delocalize the charge, and we have a way of putting spin order in there that doesn't cost energy then. In 2D, that doesn't work. So here you see this Ising-like picture of the, which is, by the way, of course, not Ising, it's Heisenberg, but it's hard to draw. The Ising-like picture around a doublon, but if this doublon now moves, we see basically that if it moves here, it has to move this spin back here, and then we get basically here frustrated or basically wrong bonds in terms of the magnetism. If it moves further, we get more wrong bonds and so on. So in principle, the energy of this complex here, basically of the hole and the wrong spins, that grows with the distance that the doublon somehow has moved in the system, and that you may say leads to basically a polaron-like structure. Basically, it can't scramble the whole system. That would cost basically infinite energy. Yeah? So it should somehow scramble the magnetism around in some fixed region. And that's basically what Fabian will talk about after me, I think, in the theory part, and Christy will talk about in a different picture of analyzing this actually as the string length from Marcus's group after the break then. And one word here, I mean, that I want to say in this whole picture, we always assume that T and J are really separate timescales, which is not true. I mean, in our case, we have a factor of 3.5 between the two. Still, let's say the observations don't match too bad, but that's probably because we are looking mostly on short distance effects here. But I mean, that was just to say the story, even if it looks very simple, is not as simple in reality. Okay, so what we do in the experiment, because given that we have this full resolution of the spins and the charges, we really can go kind of in a black box setting. I mean, it's super nice to have the theory. Don't get me wrong, Fabian. But we can also really analyze the system in a black box mind. And to do that actually in the experiment, we really want to see now the effect of itinerant, a mobile doublon, what that does to the magnetization. So let's say we want to compare to something, and that's actually a pinned doublon. So what we do now is we use this local manipulation techniques to shine in a local tweezer and fix the doublon at this position. And what you see here is basically the density. So you see basically we have unity density around that doublon, and they are density 2 basically. And we compare that to the case where we don't have this tweezer and where we just load a little bit of, well, we rise the chemical potential a little bit such that we load doublons, preferably, of course, because it's a trapped system, in the center of the trap. And so you see this enhanced doublon density in the whole central region there. So the question is now, what does this do to the magnetism? And here I think I need to explain those maps a little bit. So what we do now is basically we measure 3-point correlators. One point of the correlator is the density. So basically, where is the doublon in the system? The other point is basically a 2-point spin correlator that basically measures the strength of the magnetic bond between those 2 points. And these are these bars that you see here. So we plot these points, these maps in the sense that we always place this doublon in the center, and then we measure basically the bonds around that doublon. Yes. And then you see basically in the case of the pinned doublon, if we measure this diagonal bond strength, they are all positive, and we don't really see a big effect of that doublon in the center. If we measure the nearest neighbor bonds, again, this doublon in the center within the noise. Okay, the noise is quite large, as you see. If I don't give a color bar here, but I think it comes. We don't really see something that has a spatial dependence on the doublon here, at least in these 2D plots. So let's compare to keep you awake to the mobile case, and you see that this really strongly changes the picture. We now see that the magnetic bonds that are closest to this doublon are actually very strongly modified. They're actually sign flipped. So instead of being positive, they flip to negative. And that's a very nice, can be very nicely seen. Let me go back. In this picture, you see those here, they are positive. If this doublon moves, they become actually negative here. So that's a very strong effect on the diagonal, and that's the reason why the signal is strongest on this diagonal correlator. On this nearest neighbor correlator, you also see the signal, but it's by far not that strong or not that striking as in this case. But that's expected because of the one really, I mean, it has the motion of this thing on short distance has the strongest effect on the diagonal. We can make this, of course, now also a little bit of more quantitative by basically making a radial average around that doublon in those plots. And how do we now define the x-axis? We define that basically as the bond distance here first. So we define it basically as the distance of the midpoint of the magnetic bond we are measuring to the doublon. That is this axis. And what you see here is basically the direct comparison between the pinned doublon case and the mobile doublon case. And we clearly see a difference between the two cases that actually vanishes if we go further away from the doublon. And this is true both in the diagonal correlators as well in the nearest neighbor correlators.
Can you make measurements beyond that? How big is the lattice size in both directions? Because what happens beyond that?
Well, beyond 2.2, we basically recover the background. I don't have it on this plot. So if I plot basically the magnetic background far away from any doublon or measured post-selected that we don't have a doublon, then we are basically landing basically here. It goes, so it's really this picture, I mean, you have the magnetic everywhere anti-ferromagnetic order around the doublon. You weaken it basically. I think it's really the direct real space measurement of a polaron, if you like. Okay. Do I have still 5? Perfect. Back to 1D, because that's really something we are doing really right now, and I want to update you to what's going on in the lab now. Actually, we thought about this spin charge separation that I was showing you, if we could not also measure this dynamically. And maybe we can also bring this new aspect into the system that actually this system should actually show fractionalization, which is one of the hallmarks of this 1D systems, in the sense that we can basically make an excitation that carries a spin and a charge. For example, I kill this side out of the system. I don't know how many I put. Let's say I put only 4. That's easier to count. 2 up, 2 down. You have magnetization sector 0. I kill 1. I go either to the +1 or -1 magnetization sector. So I put in basically a spin, and I remove a particle. So I remove or put in a particle. So I also add a charge. And now, if we let the system go, we expect actually that the charge velocity somewhat proportional to t is different to the spin velocity proportional to j, and those two should actually separate such that we see after a time actually exactly one spinon and exactly one chargon in the system. And in this sense, we see basically a breakup of this initially joint quantum numbers charge and spin into two individual ones in the system. So that's what we are working towards at the moment. Because of it's technically easier, we started first with just dynamical spin-charge separation. And I'm emphasizing this now because what we did now first was basically we make a local tweezer, load a doublon, and then basically connect those chains. So we are not killing anyone out of the system, yes? And if I again make the example, 2 spins left, 2 spins right, up, down, 2 spins in the middle is magnetization 0 sector, yes? Now I connect everything. I'm still in the magnetization 0 sector. I don't kill basically a spin with this protocol. But I quench the coupling between these chains when I do that. So what I do is basically I add a charge, but I don't add a spin, but I might create an even number of spinons in the system because I quench the coupling. Yes? So it's not fractionalization, but I can still measure with this dynamical spin-charge separation because I will still see basically different velocities of the charge on the doublon here in this case, and the spinons, the even number of spinons that move out of the system. And on that we have very recent data of basically last week probably, or maybe 2 weeks ago. So what you see here is basically the system initially initialized in a doublon in the center, and then we basically connect those, click everything together, and we see basically this nice outward traveling cone. And well, because of the data is so new, I have no nice representation. You have to look on this 1.2. So that takes somehow like 1.2 milliseconds to travel something like 1, 2, 3, 4 sides. Let's see what the spin does. That takes 3.6 milliseconds to travel the same distance of sides. So we clearly see a different velocity in the charge and in the spin. And by that, basically, I think we can already say we see here dynamical spin-charge separation. What we are doing at the moment is, killing this one instead of connecting the chains. Good. I think with this, I want to finish and thank you for your attention. The summary was basically, well, from 1D to 2D to 1D. Yeah, thank you.
Yeah, so have you looked at the speeds as a function of the linear parameter? So
Not at all yet. It's really the first measurement.
So the spin charge separation should really be, there should be a ratio of the spin velocity to the charge velocity, which depends on the linear parameter.
Yeah. I can't say. At the moment what we see is roughly the ratio of T and J. What is this? Not sure what is expected. I think it must be this. I mean, it can't be off of that much. I mean, the spin has to move with super exchange, and you will see the ballistic cone, and the charge moves with the T cone basically. But I mean, in terms, we have not extracted the logical parameter or something yet.
He wants to see a demonstration of velocity. Exactly. Yeah. But a question. So, sorry.
But I was wondering. So putting this doublon there with the tweezer, to me, it sounds like it could be quite a dramatic change of the system in terms of like putting energy into it. How anti-ferromagnetic is your chain on either side after doing that?
Interesting. So first of all, in the initial state, it's away from the doublon is not affected. Yes. So we have we adiabatically pull this tweezer in at the beginning. When we raise the lattice, we lower it. So everything's fine. We see though actually a finite correlation across the doublon, which is actually because if you don't switch the coupling here, you don't cut the bonds here. Because if you still have virtual, you can actually draw that there are resonances actually. So there's still a connection, and this is why I say what this basically is a quench in the local magnetic coupling strength on those sides. But I mean, why we did this actually because we thought that is the most gentle protocol that we could do.
I would just love to see actual data. And
I can tell you it's not affected.
How is it in reality?
Yeah, I can tell you it's not affected. It's our normal. It's our normal next neighbor correlator. It's our normal next. This last week data. What should I say? It's our normal next neighbor correlator. The normal strength that we have, and we see this local weakening of this one. We see really the local defect on that one. So there's surely no dramatic effect on the system by this. I'm much more worried on the blowout, because that's resonant light. Huh? I mean,
it's really very exciting. So I was wondering whether you can put a hole instead of putting a doublon, and why and yeah.
So here, it is just because our tweezer is attractive. The new measurements we are doing is actually a hole. Because if we shoot out, it's a hole. So basically with this, we have both sides of the coin. Yeah? We have a hole, we have a tweezer, okay, the initial starting position is better. But the reason here is basically it's attractive. For the polaron, the reason is actually detection and the trap. Of course, holes are basically, they go to the side of the trap. So if they have to identify holes, that's a bit tougher because they are predominantly on the side. The other thing is, of course, we have detection errors. We have a finite detection fidelity of actually seeing the particle, seeing the atoms that have been there. So now if you identify wrongly a hole that we just lost in detection, we of course have perfect spin ordering around that because we just lost it in detection. And this effect is not there for the doublons. That's why we like the doublons much more for this, because of detection errors and because of trap effects.
So if I may just advertise, tomorrow morning I do talk about the case with the hole, and actually there's some dramatic effect actually demonstrating the fluctuating phase strings at the so I think so my question is whether in principle there's something that forbids you to detect the case of the hole with certainty.
Well, so if you, for example, if you ask me the question, can you show that hole and doublon is symmetric? I would say no, not without perfect characterization of all problems in the experiment, like detection efficiencies. I think we could see the signal also with a hole, but it will be weaker because you get all these poisonous effects from, well, detection, basically. But I mean, it depends on really the details how you ask the question, I think.
So if I look at this and I'm thinking about the whole, there are two things you can do to create a hole. You could either shoot out an atom or you could put a repulsive potential.
Yeah.
Which one of those is actually the fairer comparison to this? Because if you shoot out a hole, you've already established some correlation between the two chains. But if you put a repulsive potential, it might be different. And so I'm wondering.
Well, it's for sure different. I mean, so I think, well, are you about the difference between the hole and the doublon, or about the difference of the two methods of shooting the hole, of creating a disturbance, let's say?
Right, of the two methods of creating a hole, which one is actually the fairer comparison to this?
Well, this one would be, of course, I mean, if you would want to measure, is the doublon the same as the hole? Of course, I have to put a blue barrier. Yeah. Yes? So but that was not, that is not our intention. The intention was to show, first of all, we see different velocities and the separation of the two excitations. And the second intention, why don't we just do this? It's this aspect of fractionalization that is not here. Because of the number of spinons in this case is not conserved. The number of spinons is sometimes 0, sometimes 2, sometimes 4. It depends. I mean, it's a quench. I mean, it's really a projection of the magnetic bond strength on that, thing to the final state. So that was the intention. The intention was not at all comparing doublon to a hole, which we could also do. But I mean, you know how easy it is. You can comment to change the data.
So for the polaron, so the 2D, can one extract now either effective mass or at least mobility of the polaron?
Yeah, we thought about it. So one can think about letting it oscillate. The problem is it also disperses, of course, the doublon. And in the oscillation, you want to track the center of mass somehow. The answer is it's very difficult in 2D because of statistics. I think there's no fundamental issue with this, and it's one of the things we want to try, but it's on the scale. On the difficult side, yeah. Let's say it like this. But I think that is exactly the same. So spectroscopy is not a thing to do. So it would be really following the oscillation. That is the strength of the microscope. That's just why I say that, yeah. But in principle, yes.
Extract the information that you said in this very recent graphs. So we have dyne, we have lattice side. In the charge sector, you have the double polarization. So you're supposed to extract out a velocity.
I make a line like this, yes.
So at the very edge, and we'll say here at the end of the lattice 0, then the probability essentially is going to 0.
Here? Because of the trap, exactly.
But on the other side, you
view that as also the same way that you actually stretch the straight line here? Well, I mean, I mean, you don't put a straight line obviously on just on that. Yeah? You extract profiles. You fit somehow the onset of the front of the disturbance wave that travels out, and that we follow. But I don't exactly get the question. I can tell. So this one here will actually get locked at this distance. We can't follow it more because of that's a trap. And then actually there's another very interesting, quite funny effect. This one will go out. Because if it doesn't see the trap, the spin, I mean, you will see spin charge separation. We will not measure the velocities very nicely because of the trap in this case. But you will see it basically that the charge gets stuck in the middle and the spin it leaves the charge, doesn't get anymore. So you actually see those things as real-time slices? Yes. Moving from the center towards yes, that's what you see here basically, real-time. That's real-time slices. And that's basically the initial, so -2 basically is before we basically release it. And then you see basically at one, that's basically the distribution of the charge at just after the release, and then at whatever 0.6 milliseconds after the release. So it's somehow it's a peak distribution that widens, and because of our statistics at the moment looks like that, but that will change. Okay, so it's not the whole thing moving, but it's it's symmetrically. I mean that's because if we take the center side, that's in the track symmetry is, and that's. No, it's spreading out of the packet. It's dispersion. That's exactly the thing. That's what we see here is only dispersion, but not this. Yeah, it'd be nice to see. What's the difference? You think there's a really difference? Okay.
There's plenty of time in lunch too. Fabian is looking at me angry, but I think I don't know maybe.
Very quick question. So for like related to the trap. So in the Monte Carlo calculation that was agreeing perfectly with the experiment. Did they have to include the trapping potential, or what is the effect of the trap on the theory?
They did not have to include that. That's actually comparison to homogeneous. What we do is we have to actually a finite size correction we have to take into account, which basically gives you an offset. I don't remember actually who yesterday said that already, that if you have only a small number of spins, you know already something about your remaining spins, basically. Yeah? And that basically gives you a global offset on the correlations. But on the scale, we are looking at that basically like 3, 4, 5 sites. We don't really see more of the trap. I mean, the system in this case, the 1D systems were 20 sites long, basically, 15, 20 something. So.
And the trapping, what is the frequency of it?
Well, in this case was 200 hertz, but I mean, I think that's more at a U of I don't remember.